Dash 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 dot. Every engine running on this planet right now is built on a design philosophy that is over 100 years old. 100 years. The internal combustion engine, in cars, trucks, aircraft, industrial generators, marine vessels, and power systems worldwide, still operates on the same fundamental mechanical architecture it did in 1920. A piston connected to a crankshaft by a rod. A camshaft turning on a chain. Metal pressing against metal. Heat bleeding away into nothing. This is not a criticism. It is a statement of fact. And it is the starting point for everything that follows. The traditional internal combustion engine has three structural problems that no incremental engineering improvement has ever solved, because they are not engineering problems. They are architectural ones. Problem 1. Mechanical friction. Every moving surface in a conventional engine is in physical contact with another moving surface. Piston rings against cylinder walls. Rod bearings under load. Cam lobes against follower faces. Crankshaft journals spinning in their housings. Every one of these contact points generates friction. Friction generates heat. Heat is wasted energy. And wasted energy means fuel that was burned and paid for producing nothing useful. In a conventional engine, over 60% of the thermal energy released by combustion never reaches the drivetrain. It exits through the cooling system and the exhaust pipe. Engineers have spent a century designing around this loss: thinner oil, tighter tolerances, better coatings. The loss remains. Problem 2. Reciprocating mass. The piston assembly, piston, wrist pin, connecting rod, accelerates from 0 to maximum velocity and back to 0 with every stroke. Twice per revolution. At 8,000 RPM, that happens 133 times per second. The inertial forces required to reverse that mass are enormous, and they are structurally destructive. This is why conventional engines have a practical RPM ceiling. Beyond approximately 8,000 RPM in most configurations, the reciprocating mass generates forces that exceed the structural tolerance of the assembly. The engine does not fail because it runs out of power. It fails because it cannot survive its own momentum. Problem 3. Mechanical complexity. A conventional engine contains hundreds of precision components, each of which must be manufactured to exact tolerances, assembled in correct sequence, lubricated continuously, and replaced at intervals. Camshafts, timing chains, valve springs, rod bolts, head gaskets. Each component is a potential failure point. Each failure point is a maintenance cost, a downtime event, a warranty claim, a liability. These three problems are not separate. They are the same problem expressed three different ways. They are all consequences of the same design decision, building a machine out of parts that touch each other. Substrate vibration theory eliminates that decision entirely. The SVT engine is a magnetic levitation linear orbital propulsion system. There are no connecting rods. There is no crankshaft. There are no mechanical camshafts. There are no valve springs. There is no timing chain. What exists instead is a system in which the fundamental forces of electromagnetism perform every mechanical function that metal parts previously performed, with greater precision, at higher speeds, with zero wear, and with active real-time software control over every parameter of operation. This is not a hybrid approach. It is not an incremental upgrade. It is a complete architectural replacement of the internal combustion engine's mechanical DNA. Here is how it works. The piston in an SVT engine is not connected to anything. It is a high-permeability magnetic core, a precisely engineered slug of ferrous material, suspended inside the cylinder bore within a controlled electromagnetic flux gap. It floats. It touches nothing. There are no rings contacting the cylinder wall. There are no rod bearings. There is no wrist pin. There is no connecting rod. The electromagnetic coupling that drives and controls this core operates on what is called the phase shift decoupling cycle, or the instantiate, release, catch protocol. At top dead center, 0 degrees of crank rotation, the system engages. A high voltage, quantized electromagnetic pulse fires through the inductive coil matrix surrounding the cylinder. This creates a maximum repulsion field that acts as a virtual rigid member. It catches the peak combustion pressure and drives the magnetic core downward with the same function a connecting rod would perform, but without the connecting rod. As the core begins its downward power stroke, from approximately 10 degrees to 170 degrees of rotation, the system immediately drops the electromagnetic field to zero. The core ghosts. It travels down the cylinder bore under the momentum of combustion pressure alone, with zero magnetic drag, zero mechanical friction, and zero resistive force of any kind. The cylinder is, in effect, a frictionless environment during the power stroke. At bottom dead center, 180 degrees, the system re-engages with a phase-inverted counterpulse. The control computer has been reading the precise micrometer-level coordinate position of the core throughout the entire stroke. It fires a precisely timed inverted field that catches the core's downward kinetic momentum, cushions the transition, and initiates the return stroke. This is not theoretical. This is the same operating principle as a linear particle accelerator, applied to a piston engine. And here is where the architecture generates something no conventional engine can. The system harvests its own operation. During the initial engagement pulse, the mechanical acceleration of the magnetic core moving away from the coil matrix forces the local electromagnetic field apart. This mechanical compression of the field drives a current surge back into the system's capacitor banks through standard electromagnetic induction. The governing equation is Faraday's law of induction. The induced voltage equals -N times the rate of change of magnetic flux. The engine does not just consume power to run. It feeds power back into itself with every stroke. The SVT engine eliminates mechanical valve springs, replacing them with a sealed, isolated pneumatic containment cell pressurized with a precisely formulated gas matrix. The stoichiometric composition of this gas matrix is 1.5 parts nitrogen, 4 parts hydrogen, 2.5 parts helium. Each constituent element is selected for a specific thermodynamic function. Nitrogen provides the structural density baseline. It establishes the foundation pressure floor and acts as a chemical buffer, preventing molecular dissociation under the high shear forces generated during rapid cyclic compression. Hydrogen, comprising the largest portion of the mixture, serves as a high-performance thermal heat sink. Hydrogen has the highest thermal conductivity of any gaseous medium. During rapid compression cycles, the hydrogen component absorbs adiabatic compression heat and transfers it directly to the cylinder head cooling jacket, keeping the valve seat interface thermally stable at operational frequencies that would cause conventional springs to experience float. Helium is deployed for its acoustic properties. As a monatomic gas, helium conducts sound at approximately 3 times the velocity of atmospheric air. This means that when the valve stem retracts, the pressure behind it restores to equilibrium nearly instantaneously. The snap-back is not linear. It is progressive and nonlinear, outpacing the mechanical response time of any steel coil spring configuration at any RPM. The result is a valvetrain that cannot float. There is no RPM ceiling imposed by spring resonance. The gas matrix responds faster than any mechanical component can. Containment of the hydrogen and helium matrix, two gases known for their tendency to permeate conventional sealing materials, is achieved through the Leidenfrost effect. A specialized synthetic oil layer is introduced continuously at the valve guide boundary. As the engine reaches operating temperature, the radiant thermal energy from the combustion chamber vaporizes the innermost microscopic layer of this fluid against the hot valve stem surface. This creates a continuously self-generating, self-healing high-pressure vapor cushion. The valve stem rides exclusively on this vapor cushion. Metal-to-metal contact at the valve guide interface is zero. The hydrogen component of the gas matrix bridges the vapor barrier thermally, preventing the insulating effect that a standard vapor layer would create, and maintaining stable temperature equilibrium throughout the interface. Friction coefficient at the valve guide, 0. Wear rate, 0. Maintenance interval, indefinite. The overhead camshaft, with its fixed lobes, fixed timing, fixed lift curves, and inherent limitations on variable valve control, is replaced entirely by the linear induction valvetrain, or LIVT. The LIVT is a closed-loop, railgun-style linear induction track running along the cylinder head assembly. The track is lined with sequentially addressable electromagnetic stator coils. Operating within the track are independent Ferris carriers called magneto shuttles, ultra-lightweight, with no physical connection to each other, controlled entirely by software. A software-defined charge wave fires down the stator rail, accelerating the independent shuttles along the track. As a shuttle passes over the cylinder head, its physical profile engages the valve lifter directly, opening the valve against the gas matrix spring. Because the charge wave is entirely software-defined, the control system can accelerate, decelerate, or hold a shuttle stationary above any valve at any point in the cycle. Valve lift, duration, and timing are not fixed. They are infinitely variable in real time, adjustable on a per-cylinder, per-stroke basis in response to load demand, fuel composition, thermal state, and performance target. This is not variable valve timing as it exists in current production engines, a mechanical system with several discrete positions. This is fully continuous, software-governed valve control with no mechanical constraints. In the event of an emergency over-rev condition or component fault, the control system instantly de-energizes the stator rail. The charge wave collapses. The shuttles disengage. The gas matrix springs close all valves simultaneously. The engine protects itself without requiring any mechanical intervention. Conventional electromagnetic shielding operates on a blocking principle. External interference is deflected. The Dragnet resonance system operates on the opposite principle. The resonance chamber, constructed of graphene layers and carbon-13 isotopic doping matrices, is tuned to function as a harvesting net rather than a shield. Ambient electromagnetic energy from the operating environment, EMF noise, radio frequency emissions, industrial interference, solar flux, is actively drawn into the resonance chamber via the Dragnet dynamic rather than deflected away from it. Inside the chamber, the phononic bandgap array of the graphene carbon-13 lattice focuses and channels incoming electromagnetic flux lines, increasing field density and drag efficiency. Captured energy is compounded within the resonance chamber and fed back into the system as usable electrical potential, increasing coherence and system output. The engine does not operate despite electromagnetic interference. It operates better because of it. The SVT engine achieves a maximum operational RPM in excess of 20,000. This is not a theoretical ceiling imposed by the architecture, it is a current benchmark. Without reciprocating mass, without valve float, without mechanical friction, there is no inertial constraint on rotational speed. Power density is 3 to 5 times greater than a conventional internal combustion engine of equivalent displacement. Thermal efficiency is 98.4%. Near-zero carbon emissions under standard hydrocarbon fuels, with full compatibility with hydrogen, alcohol-based fuels, and hybrid fuel matrices via the programmable stoichiometry injection system. Maintenance requirements approach zero for the core mechanical architecture. There are no wear surfaces. There are no consumable components in the drive system. There are no timing belts to replace, no rod bearings to fail, no valve springs to break. The SVT architecture is not a single product. It is a scalable propulsion framework. At the micro scale, the electromagnetic coupling and gas matrix spring systems reduce to ultra-compact, high-precision motors suited to surgical robotics, advanced drone propulsion, and precision industrial automation, applications where conventional motors cannot achieve the required combination of speed, precision, and zero-maintenance operation. At the macro scale, the SVT engine replaces the conventional internal combustion engine in automotive, marine, and industrial power generation applications. The same architecture that produces near-zero emissions at street-legal power output scales directly to high-performance applications without architectural modification. At the mega scale, the phased stoichiometry combustion system extends directly to the EPEKIS aerospace thruster concept, a propulsion architecture capable of sustained thrust at velocities approaching 26 miles per second. The Leidenfrost vapor barrier and gas matrix technologies that manage thermal loads at automotive scale are the same technologies that manage the extreme thermal environments of aerospace propulsion. 1 architecture. 3 orders of magnitude of application. The question is not whether this technology works. The electromagnetic principles are established physics. The Leidenfrost effect is documented and industrially applied. Linear induction propulsion operates in production environments worldwide. The gas matrix thermodynamic calculations are verifiable. The inductive capacitance harvesting is governed by Faraday's law. The question is whether the industry is ready to stop engineering around a 100-year-old architectural limitation and replace it entirely. The SVT engine is that replacement. No connecting rods, no camshafts, no valve springs, no friction, no sealing. The future of propulsion is solid state.